Welcome to today's lesson. Today we are going to learn the structural design of rigid pavement. For rigid pavement on concrete pavement, it normally has a concrete base, a subbase, and a subgrade underneath. In the previous two lectures, we have learned the structural design of flexible pavement. Now let's focus on the structural design of rigid pavement or concrete pavement. Concrete pavements may be used in all urban classes of road pavement and moderate to heavily trafficked rural road pavement. There are mainly four principal types of concrete pavements: plain or jointed and reinforced concrete pavements, PCP; jointed reinforced concrete pavements, JRCP; continuously reinforced concrete pavements, CRCP; and steel fiber reinforced concrete pavements, SFCP. There is also another type of concrete pavement, the pre-stressed concrete pavement, but we are not going to discuss its design procedure in this lecture. Now let's look at the details of each type of above four concrete pavements. As shown in the graphs are the top view and side view of the plain, jointed and reinforced concrete pavement, PCP. In plain concrete pavement, reinforcement is sometimes necessary to control cracking. The slabs are normally 4.5 meters long with doweled square joints. The dowel bars are placed at the transverse joint of concrete pavement, and they take part in partial wheel load transfer from one slab to its adjacent slabs. The dowel bars allow actual thermal expansion and contraction of the concrete slab along the axis of the dowel. Slabs are reinforced if it is anticipated that cracks could occur due to stress concentrations, which can't be avoided by rearrangement of the slab joining pattern. The plain concrete pavement have to be reinforced in discrete areas, such as odd-shaped and mismatched slabs and in base anchor slabs. Also, typical spacing between transverse joint is 3.7 to 6.1 meter, as shown in the figure. In the longitudinal direction, the tie bar is normally used. They are the connectors used for holding faces of rigid slabs in contact to maintain aggregate interlock. Unlike dowel bars, tie bars do not transfer the load, so that's the major difference between them. The jointed reinforced concrete pavement is normally mesh reinforced with doweled joints spaced between 8 and 12 meters and up to 15 meters, as shown here. The transverse joints are perpendicular to the direction of travel. Intermediate cracks are expected to form at about 4 to 6 meter spacing and often within days of paving. In JRCP, the purpose of reinforcing steel or reinforcing mesh is not to prevent cracking of the concrete, but to hold tightly closed any cracks that occur in such manner that the load capacity of the base is preserved. If suitable reinforcement is provided in a slab of acceptable proportions, cracks should not require any treatment during the pavement design life. Compared with the JRCP, the CRCP is an integral cast. It does not have dowels and tie bars, so more cracks are generated. For CRCP, sufficient continuous longitudinal steel reinforcement is provided to induce the desired transverse cracking at random spacings of about 0.2 to 2.5 meter, and then hold these cracks tight. So no need the contraction joints. The contraction joint is a transverse joint to control cracking due to pavement contraction caused by shrinkage and temperature fluctuations. The left figure is the side view, and right figures are the top and side view. The transverse reinforcement is provided to support the longitudinal steel. Transverse steel also provides insurance in the event of unplanned longitudinal cracking. This is a great way to make a pavement really strong and capable to support tremendous loads. It's also very expensive, and when the day comes, when the pavement has to be demolished, it makes for a nightmare for the demolition crew as the steel continues to perform its job of holding the concrete together. The last one is the steel fiber concrete pavement, SFCP. Steel fibers are typically between 15 millimeter and 50 millimeter in length, with either enlarged ends that act as anchorages and or crimping to improve bond. Typically, fibers are added to the concrete at a rate of approximately 45 to 65 kilograms per cubic meter. It provides improved resistance to cracking, and it is ideal to areas with a high percentage of irregular slabs. Because of the increased flexibility in the design of the joint layout, such type of concrete pavement is the only option for intersections and roundabouts. This type of pavement is also often used for toll plazas and bus stops. Now let's look at the concrete shoulders. It provides a lateral support to the main slab of pavement and also results in additional stiffness. The concrete shoulders improve the pavement performance and enable a lesser base thickness to be adopted. The concrete shoulder must be either integral or structurally tight to satisfy the width shoulder criteria. Substantial curves such as urban curve and channel can be considered to provide with shoulder support, provided that they are constructed of structural grade concrete of strength consistent with the pavement, and they are effectively tied to the pavement, and the joint has a corrugated face for load transfer. In terms of subbase or rigid pavement, House rules recommends lean concrete subbase or bond subbases. A bond subbase is composed of either cement stabilized crushed rock with no less than 5% by mass cementitious content. This is to meet erosion resistance requirement. Other types of bond subbase are dense graded asphalt or rolled lean concrete with characteristic 28-day strength of equal to or greater than 5 megapascal. Once we have the design traffic entity, the selection of the minimum subbase type is determined from table 9.1. According to different calculated NDT, we choose different type of subbase from this table. Within the table, the LCX stands for the lean concrete subbase. So if the design traffic is greater than 1 to the power of 1 times 10 to the power of 7, and for continuously reinforced concrete pavement, CRCP. A heavily bound subbase with an asphalt surface is deemed as an acceptable alternative to LCS. Now let's see the factors in thickness determination. Similar as that for flexible pavement, for rigid pavement thickness design, the strength of the subgrade is also assessed in terms of CBR. All materials within 1 meter below the subbase must be evaluated to determine the design subgrade CBR. It is also required that the selected subgrade material ought to be consist of a uniform, volumetric, stable material that is constant for the service life of the pavement. The corresponding CBR has to be at least 5%. Another factor for thickness determination is equivalent subgrade strength. For 1 meter underneath the subbase, the subgrade design CBR must be determined based on a multi-layered subgrade system. The equation 25 could be used to determine the equivalent subgrade strength CBRE based on the strength of the supporting soil, where the CBRI is the CBR value of the S layer. HI is the thickness of the S layer, and EHI is equivalent to a depth of 1 meter. There are some conditions to follow when using this equation. The layer with thickness of less than 200 millimeter must be combined with an adjacent layer, and the lower CBR value must be adopted for the combined layer. It is also assumed that higher CBR materials will be used in the upper layers. The formula is not applicable where weaker layers with smaller CBR are located in the upper layer. In other words, the magnitude in terms of CBR has to be in descending order. If there's any filter layer, then it must not be included in the calculation. Finally, the maximum CBR for the use of this formula is 15%. So that's for the 4 conditions we have to follow when using this formula. Now let's look at one example. We need to determine the equivalent CBR of the stratified subgrade as shown in the diagram below. Firstly, because the layer thickness of the top 2 layers are less than 200 millimeter, you see the first layer and the second layer, both less than 200 millimeter. So we need to combine them to form 1 layer, and the lower CBR value is used for the new layer. So that's the new layer thickness. That's the corresponding CBR. After this, all the previous conditions of equation 25 are met. The equivalent subgrade design strength CBRE could be calculated using equation 25. And after we plug in all the values into this formula, we get the CBRE of 4.7. The effective subgrade strength also influences the thickness determination. So the composite strength of the subgrade and the embedment soil below it is termed the effective subgrade strength. So previous research and experience has indicated there's an increase in effective subgrade strength with the use of bond and lean concrete subbase. The red figure, the figure 9.1, could be used to determine the effective subgrade strength using the base thickness design. We will talk more about this figure in the later part of this lecture. But now The factor in thickness determination is base concrete strength. Normally, the 28-day characteristic flexural strength of the concrete is used as the design strength. Also, we have the requirement that the minimum characteristic design concrete flexural strength with design traffic of 10 to the power of 6 HVAG or more is 4.5 megapascal at 28 days. And for steel fiber reinforced concrete pavement, it is 5.5 megapascal. We know that for concrete base, normally it needs long curing time to gain the strength. But tracking paving construction technique is a viable option for new and rehabilitation pavement construction. This is because it allows traffic to resume on the concrete within 24 hours of paving. The final factor is the project reliability. During design, the actual group loads are multiplied by a load safety factor, LSF, or specified rigid pavement type. For PCP and DOT and CRCP, here the DOT mainly represent the joint reinforced concrete pavement, JRCP. The LSF can be taken from the table according to the project design reliability in between 80% and 97.5%. The load safety factor provides a certain degree of conservatism by allowing for the possibility of unpredicted heavy truck loads and a higher level of pavement serviceability. For flexible pavement, we consider 3 distress modes: the fatigue damage to asphalt, fatigue damage to cemented material, and subgrade rotting and loss of surface shape. To determine the thickness of rigid pavement, we followed the Portland Cement Association method from USA. It is an old method, but still commonly used in modern days. For the base thickness design of the rigid pavement, 2 distress modes were considered: the flexural fatigue cracking of the pavement base and subgrade or subbase erosion from repeated deflections and joints and planned cracks. For flexible pavement mechanistic design, we have to follow 18 steps, where for rigid pavement design, we need to follow 19 steps. Firstly, we have to select a pavement type, then decide whether tied or integrally cast concrete shoulders are to be provided. Next is to determine the subbase thickness and type of and effective subgrade strength. Afterwards, we need to select the 28-day characteristic flexural strength of the concrete base, FCR, and then select the desired project reliability and the load safety factor. Step 7 is to select a trial base thickness. Then we calculate the expected load repetitions of each actual group load of each actual group type. From the traffic load distribution, we find the highest actual load for the SASD actual group and determine the allowable repetitions in terms of fatigue. Then we calculate the ratio of the expected fatigue repetitions to the allowable repetitions and determine the percentage of fatigue by multiplying 100. We also need to work out the allowable number of repetitions for erosion for the highest actual load for the SASD actual group. Again, calculate the ratio of the expected erosion repetitions to the allowable repetitions and find the percentage of erosion damage by multiplying 100. Step 9 to 12 will be repeated for each actual group load up to a load level where the allowable load repetitions exceed 10. Afterwards, we sum the percentage of fatigue for all relevant loads of this actual group and the percentage of erosion for all relevant loads of this actual group. Step 9 to 14 will be repeated for actual group type. Step 16 is to sum the total fatigue and erosion damage for all actual group types. Then steps 9 to 16 are repeated until the least thickness that has both total fatigue and total erosion damage less than or equal to 100% is determined. That thickness will be the design base thickness. We also need to meet the minimum base thickness requirement from table 9.7. Lastly, we confirm the final design base thickness and consider the potential application of additional thickness tolerance. So in short, a trial design base thickness is selected and the total fatigue and erosion damage is calculated for the entire traffic volume and composition during the design period. So if either fatigue or erosion damage exceeds 100%, then the trial thickness is increased and the design process is repeated. The design thickness is the least trial thickness, which has a total fatigue less than or equal 100% and a total erosion damage less than or equal to 100%.